How do extensive properties work in thermodynamics? Imagine you have a big jar of honey. If you take out half of it, the amount of honey left is less, but the total amount you had initially was more. This idea is similar to how extensive properties work in thermodynamics. These properties depend directly on how much matter is in a system. If you increase the amount of material, these properties grow proportionally. Think about mass. If you have 1 kilogram of water, that's your mass. If you double it to 2 kilograms, the total mass doubles too. The same goes for volume. 1 liter of water is a certain size, but if you combine it with another liter, you now have 2 liters. These are simple examples, but they show how extensive properties add up when you combine systems. Other important extensive properties include internal energy, which is the total energy stored inside a system, and enthalpy, which relates to heat content. Entropy, a measure of disorder, also depends on how much matter you have. When you add more gas into a container, the total internal energy increases because there's more energy stored in the larger amount of substance. A key point is that dividing one extensive property by another often gives you an intensive property. For example, if you divide the total mass by the total volume, you get density. Density does not change just because you have more or less material. It stays the same for a given substance. This is because density is an intensive property, meaning it does not depend on the size of the system. Knowing how extensive properties work helps scientists and engineers figure out how much energy, mass, or volume is involved in physical or chemical processes. When they analyze systems, they use these properties to calculate total energy changes or total work done, which all grow with the size of the system. In simple terms, extensive properties are like the total score in a game. They depend on how many points or items you have. The more matter you add, the larger these properties become. They are essential for understanding how systems behave and how energy moves around in the world of thermodynamics.